Okay, thank you. So this morning I will continue to talk about 3D system integration, and after the presentation from AMD, of course, I'm not going to say something completely different, as you might imagine. When we look at this field of 3D integration for system integration, we have technology and you have system aspects, and we need to reconcile these two type of elements. And as was shown in the previous presentation, the track record of semiconductor technology has been very significant in scaling down dimensions of devices, making them ever smaller. But of course, there are some challenges where, from the physics part, gate length scaling stopped, or you have metal pitch scaling limitations. So we have always been faced with these challenges in regard to scaling, and lithography, of course, and all the evolutions of lithography have enabled us to still continue that roadmap very successfully. And as already was pointed out by the previous presentation, it's not only the lithography that makes a difference, it's also the fact that a lot of innovation has happened, and the smart engineers that come up with new ideas, such as the copper low-K, the high-K metal gate, the FinFETs, the nanosheet devices, and for the future, maybe the 2D channel devices. So we are in a pipeline to continue this story for the coming decades. So the end of scaling has always been near and will remain always near, probably. So that's continuing. We're continuing to increase complexity. However, at the same time, we also see, when you look at system performance metrics, that actually the performance of single threads performance in computers is actually stalling, it's going down. And of course, we solve that at the system level by putting in more cores. But putting in more cores means more interconnectivity challenges, and that brings us to what we call the memory wall, and how to connect more devices to the same memory in a consistent way. The other part is that all these transistors consume energy, and if we do not scale properly, you actually do not scale energy, and the energy goes up. So already previously we have seen flattening of clock speeds on chips. Basically because, to some extent, the power dissipation on the chip has been limited to something like 100 watts per square centimeter, which is kind of a power wall. Another one of the challenges engineering has to overcome to enable higher performance. So CMOS continues to innovate. We are challenged, increasing complexity and cost. Access to memory, the memory wall, cooling, heat removal is the power wall. Actually, should also add, next to heat removal, it's putting the power in as well. It's also a challenge. If your device is thousands of watts and it works sub-volt tension, that means 1000 ampere that is going to go to your chip, so you need a big cable to connect to that. So that's not so straightforward either. We believe, as many do today, that multi-chip heterogeneous integration is an important factor of solving these problems, where we repartition the system. So the system on chip concept is being changed from a purely monolithically integrated system to a more diverse heterogeneous system. And then we need a very high density fabric, interconnect fabric, to bring all these things together again, actually kind of fooling the system to think that they are still on one chip, although they are on multiple chips together. We have seen a lot of drivers in the industry for 3D integration technology development. The original one, I should say, is from the CMOS imager type of front, where backside illuminated imagers and multi-layer stacked imager devices paved the way for a lot of the technologies that we take for granted today, such as wafer-to-wafer bonding, ultra thinning of silicon, for instance. This is a field that continues to advance, and actually from just capturing images is merging to another field, which is creating light, like micro LED for augmented reality. So it is a kind of similar type of technology driving further innovation in 3D integration. As was already mentioned, HBM is another strong driver for 3D integration. It was the first products to be using like TSVs and device stacking. It's continued to increase in complexity, adding more chips in a single stack, which has significant technical challenges by itself, and also increasing in bandwidths to very high bandwidths, and that's continuing as well. And that was used, like previous speaker clearly showed, to bring those memories together with complex SoCs to make very high-performance systems. And today, as also was shown, up to 6 of these HBMs around a single SoC die. And you have to consider that 6 HBMs may be up to more than 50 chips, actually, that are surrounding your single chip. So one HBM is not one chip. So if people wonder about the cost of an HBM, why it's expensive, if there are 12 dies inside, you have to consider that aspect too. There are also some new emerging applications. A lot has to do with this discussion on chiplets, where a lot of effort is being spent today in trying to standardize or to agree about some kind of standard for communication between chips, whether it's AIB, BOW, UCIe. There's a lot of traction on these standardizations. You need technologies to go with that, things like silicon interposers, silicon bridges, high-density RDL, because you need very, very high-density interconnects to make them work with low power consumption. There is also SoC repartitioning, and I think the previous speaker showed the key example in production today, where you take actually L3 cache and you put it on top of the chip. This is actually, to my view, a bit different than the chiplet architecture, because you're not having any 2.5D bus interface. You're really going directly straight to the other chip as if it would be on the same chip. So you're succeeding even better in fooling the system that it is on the same device. Other things that are happening is in the memory space in 3D NAND, where because of the complexity of fabrication, creating the multi-tier stacks, the hundreds of layers of NAND bits, and at the same time making performant peripheral logics is challenging. One way is to make wafers with only the memory layers, and other wafers with the periphery logic, and then bonding them together using wafer-to-wafer bonding to make 3D NAND stacks. And that type of technology is now on the roadmap of all the 3D NAND companies today. And then finally, I also would like to add another technology in that frame as emerging technology, which is the backside power delivery. If we need to deliver all that power to the devices, we need to go closer to the devices, as the power delivery through the regular back end of line has its limits. And one of the ways is to actually go directly with what we call nano TSVs, directly at the level of the standard cells to power the devices in your logic device. So a lot of new innovation and new adaptation of 3D integration technologies. And I would say there are two main industry directions today. The more pragmatic thing to do today with existing technologies is what we call the chiplet 2.5D technology and some 3D technology. It's using standalone design of chips interconnected through a standardized bus interface. That is typical type of construction for this. Whereas the the other approach is a 3D SoC integration, as I would call it. This is designed as a SoC, so it's a single design interface for the designer, but you partition in different layers. So you do place and route of standard cells on different levels of the device. So in that case, you use the on-chip interconnect fabric and bus systems to connect the chips together. You don't use kind of an external bus structure. And that, of course, goes much deeper to the lowest levels of your device. It goes not just at the level 3 cache, but goes to level 2 and even level 1 cache systems. So some discussion now on the chiplet integration first, and then I come back to the 3D SoC requirements and technologies. So if you really take a very, let's say, remote view on what the chiplet actually does to your chip, is that it's actually going to add an additional block on the chip, which is this PHY interface circuit that will actually make the communication between the internal chip structure to the outside and then go to the other chip through that standardized bus interface, where it will have a similar other block on the other side to translate again into the logic of that other chip. So there is always these blocks associated to that. So that means there is inherently some latency induced, not only by the interconnect, that may be actually the smaller part, but definitely by the PHY blocks themselves. The other things you have to wonder is that these little blocks may be actually not so little, because they may consume a lot of area on your die as well. So these standardized chip interfaces, and there are a lot of discussions on that for which standard to use and go forward. So we could say that actually what is existing definitely today as a kind of chiplet interface in real volume production is the HBM interface. It's actually very similar. That type of interface also connects through a PHY from the chip to the memory. It's characterized by a very big forest of bumps with many, many lanes of connections. And what you can see there is that if you want a 1000 wide bus, 1000 channels, that actually when you look at it at the end, you have 50% more channels because you need things like clock forwarding and error correction and communication. So there is actually quite some significant overhead. And the result of that is that the pitches you need for connecting these chips together in the interconnect are really tight. If you do the interconnect in a single layer, you're down at 3.5 micron for pitch for the channels in this case. And this is just because of the sheer number of wires that you need to connect. What is also quite clear is that a lot of the bumps in the array are actually for power and ground, especially at higher speeds. This is very important to maintain a good integrity of the signals and provide the power directly to the driver transistors. So there's a lot of open source chiplet proposals, which makes it, of course, quite interesting for the general industry to adopt this type of chiplet interfaces. So as I mentioned already, the chiplet interface is this forest of bumps with very dense wires. The bandwidth is actually very simply defined by the bandwidth of a single channel and the pitch divided by the pitch of the channel. So the smaller the pitch, the higher the bandwidth we can achieve for a certain length of the width of the bus. If we want to achieve something like 2 terabits per second per millimeter as a bus, it's clear that if we work at a 4 micron pitch technology, the kind of speeds you need would be 8 to 12 gigabit per lane. If we have a technology that can do much finer interconnects, let's say 2 micron pitch, so 1 micron line in space, that requirement drops obviously by half to 4 to 6 gigabit per second per lane. So that also means that a coarse interconnect technology will result in a more complex circuitry to go to higher frequencies to make the transition between the chips if you really want to achieve a high bandwidth between the two chips. Using high performance interconnect technology lowers the requirement for the bus speed per lane. Because on the chip you have lower speeds and you're actually multiplexing to higher frequencies because you want less wires than on the chip. The bump array itself that is used, if it uses big array, has a certain size which is also quite significant. And actually, again, this area that is consumed on the chip is to a large extent defined by the bump array. Especially if you're at, like in HBM, you may have like a width of that array of bumps of something like 2.7 millimeter that you use. So it's quite significant number of square millimeters that you're actually needing on your chip to make the interconnects if you're using a coarse pitch connectivity. So if we go to smaller pitch connectivities, if you like instead of going at 60 micron pitch for bumps, we can go to 20 micron pitch. That's immediately reducing the length of that additional wiring and the area on the chips by a factor of 3. So it has a very strong impact of technology choices on actually the area consumption or the speed that you can achieve. The other element is about power, which is already mentioned before, is quite important. And in such a bus architecture where you want to achieve a certain bandwidth, actually the power to first order is defined by the FCV square rule. So for depending on how you organize the structure, but you basically have a power that is related to the bandwidth of the bus you want to achieve, multiplied by basically the capacitance in the system, which is the microbump capacitance, which scales again quadratically with the size of these bumps, and with the additional length you add because of the size of these bumps. And that's actually often for high density becomes dominant. So also there, bump pitch scaling is important to reduce power consumption. The other important element there is that the SerDeSes that go to higher frequencies, the higher the frequency you have to multiply, the more power they will consume. So there's also a negative, strongly negative effect of going to too high SerDes frequencies on the power consumption at the system level. So from a technology perspective, how to best organize that interconnect? Of course, what many people have been using so far are silicon interposer chips. Silicon interposers, they offer the highest interconnect density. They're basically using back-end-of-line technology, established type of back-end-of-line interconnect technology. They can easily go to the micrometer pitch level if needed. And it also offers to scale the microbump pitch. You don't have to do microbump pitch at 100 micron, 50 micron when you do silicon to silicon, because there is a CTE matching between the two substrates, so it allows you to go much deeper. So that is an opportunity with silicon interposers. But as already mentioned, if your system becomes very big with many dies on that interposer, it may become multiple reticle sizes in area, and then it also gets quite costly. And you're really only using the high bandwidth to go from one die to the neighboring die. So that's why silicon bridges are interesting in this respect, where you limit that fine pitch connectivity to the borders of the chips, bringing them very close together with a silicon interposer bridge. And by the way, that silicon interposer bridge can also be active. It could also have repeaters if necessary, so further improving possible functionality. The alternative from a low-cost perspective would be to use a very fine-pitch RDL technology, if that is possible, and then flip chip the die on the RDL, so kind of RDL first technology with flip chip last integration, a kind of fan-out package. That requires extremely fine RDL technology. So at imec, we've been working on both of these technologies for several years. So in the area of silicon bridges, we've been looking into technologies where we first place the die on a temporary carrier, bond silicon bridges to these chips, and then perform molding and back grinding. So it's a very direct approach to realize the bridge connection between the dies by using plated copper bumps on the chips. After back grinding, you expose them. You can do further processing of RDL or bumping on that side. We even did this with chips that contain TSVs, so we can put on the backside even additional chips and make a kind of a 3D fan-out wafer-level packaging technology that way. The other part of these things is the RDL technology. RDL technology typically is what we call semi-additive. You deposit a seed layer, a photoresist, you plate up the copper, and then you etch away the seed layer after stripping the resist. That has challenges with respect to CD control when you get to very fine structures, but it is possible to go to 2-micron line and space. What is more difficult is to make via connections between layers that are really matching those lines. So they are typically bigger vias that require bigger pads to land the vias. So there is some loss in connectivity because of this TSV, these large via structures. The alternative is to actually take the Q from the back end of line and to move into a Damascene RDL technology, and that is also possible. In this case, we're not depositing oxide and dry etching it. We're actually depositing a negative wafer level RDL dielectric, photopatterning it to make vias and making another layer to make trenches, to make lines. And in that way, we can go to smaller lines and spaces. Below a micron is even possible. And also, we can make vias that fit the lines. So we can take similar design methodologies, PNR, place and route type of configurations as in the back end of line of the chip. And that, of course, may be a bit slightly more complex way of integrating RDL, but the number of layers you will need for a complex integration flow are reduced, so it can still be, we believe, cost effective. Also that, because this is flat, it's using CMP to make the connections, you can build up as many layers as needed without topography issues. The other part that goes with this has to do with the micro bumps. So traditional industry micro bumps use kind of copper pillars with nickel and then some reflown tin silver solder. That is typically coming from the assembly to laminate. It's a technology that's characterized by a relatively large standoff height. We have shown that it's possible to scale that down, that type of technology, to something like 20 micron when you move from a reflow type of soldering technique to thermocompression bonding, where we plate the bumps without reflowing them and make this kind of structure with smaller solder-based bumps on the top and larger pads on the bottom. And more recently, we also been working to scale that down to 10 and even below 10, 7 and 5 micron by using what we call embedded micro bumps, moving from a copper UBM to nickel-based UBMs to minimize the consumption and maintain the reliability. Because this is silicon to silicon technology, you are allowed to scale the micro bump. If you do micro bumping to a laminate with a big CTE mismatch, then you have more issues with respect to reliability. In the field of 3D SoC, which is a bit of a different area, we are not going to make separate chip and then put them together with a standardized bus interface. Now we're going to design as if it's a single die. And the classical example of it is to partition memory layers, but the deeper memory layers, on another level of the chip, and to co-design the place and route of the memory and the logic cells. And this indeed requires a different thinking from the designer, because now in a typical 2D flow, your IOs of your IP block would be at the edges of this IP block. If you think in 3D, you actually would prefer them to be in the center of the block rather than at the edges to reduce, for instance, internal delay in the memory blocks or in the functional blocks. So there is some rethinking necessary. It's also important that the EDA tools are being, let's say, adapted, because it means that during the design you have PDKs of different technologies present at the same time in your design flow. And this is now finally getting, let's say, into the market. We've been working with Cadence on that topic for many years, which is now enabling first the EDA tools that can do PNR in multiple levels in an efficient way. So one way to think of it is if you have your multi-die single 2D SoC chip today, you could say I could partition memory in a separate specialized chip technology. I do logic in the advanced logic technology, and then I take another chip on the bottom for my I/O, because that is not scaling, of course, and you also do crossbar interconnect and power delivery functions in that bottom die. You could take the logic wafer, process it up to the almost top layers, not fully the top layers, and there you provide a layer with copper hybrid bond pads. Those copper hybrid bond pads will be bonded to copper pads on a memory wafer. So this could be, for instance, an SRAM only wafer, so could be probably with reduced complexity from the point of view of number of metal layers. You bond these two together with wafer-to-wafer bonding. So now everything, all the action is in the center of two thick silicon wafers. So we need to thin one side, and we choose to thin the logic side to a very thin silicon layer, where we can make nano TSVs to do the backside power delivery network connections to the device, and then provide the fat metal layers you typically have on top of the wafer that deliver the power to the system, actually to put them on the backside, which is the new front side. At that stage, you can flip chip that die on a bottom die, which is your I/O fabric die. Okay, so you can do this in different ways. So this can be, you can do it simple with two partitions, but there can be more of them as well, because you can partition level 2 cache that way, but you can even go down, if you go to very small interconnect density between the layers, to level 1 cache that you can separate from the core, so making the system even more compact. Of course, this type of composite chiplet, I would say, is not going to stand by itself. So these chiplets could be mounted on this interconnect fabric die as a kind of active interposer, which is then connected with silicon bridges to, for instance, HBM die that provide the memory compute outside large caches, but also with optical I/O modules that provide the connectivity to the rest of the systems, referring to like the systems like the previous presenter with the big racks and communication between these chips. There photonic-driven interconnects at that scale are definitely a must requirement to actually get the bandwidth to these computational beasts. The technologies that you need to build this are based on this hybrid bonding technology. At imec, we have been working on a hybrid bonding variant using silicon carbon nitride as a bonding dielectric and copper pads. Silicon carbon nitride is known from the back end of line for its compatibility with respect to copper diffusion, for instance, and electron migration resistance for back end of line structures. It's kind of a passivation layer, so it's a barrier for moisture and oxygen to go through. It's also a bit harder layer, so after CMP, this is extremely smooth layer, so it provides high bond strength directly from the room temperature bonding. And it provides also capabilities to limit the post-bond cure temperatures, annealing temperatures to something like 250 degrees C. So we've been able to show and publish data on scaling down to 700 nanometer pitch with this technology. And currently we're working on technologies to go down to 400 nanometer pitch interconnectivity between the wafers. When we're reaching this 400 nanometer pitch connectivity, you can do very different things from a design point of view. And so going down in the scheme of dimensions actually enables very new architectures to be realized, particularly if we think that you have like level 3, level 2, level 1 caches. This is a hierarchy in density that you require, which is almost scaling exponentially when you go to the deeper levels closer to your devices. And it's also a moving target because the standard cells you're connecting to are also scaling at the same time. This wafer-to-wafer technology is now of high interest to also adapt to die-to-wafer, and AMD really is the pioneering company to put this into practice for the first time, together with TSMC. It's much more challenging, so you could say it's the same challenges, but you need to singulate the dies, and particles are your worst enemy because a particle between the die and the wafer you put it on will create a defect which is several orders of magnitude bigger than the particle. So a very tiny particle blows up to a big defect. So using this approach, we have done what we call collective die-to-wafer bonding solutions, going down to 5 micron pitch for the connectivity using intersecting line segments, like shown in this case. And we also plan to go down in that scaling range towards 2 micron. So die-to-wafer hybrid bonding, we believe, has this sweet spot of application in the 10 to 2 micron pitch range. So the direct bonding, which is picking up the die and placing it on the target wafer, is the most direct form of die-to-wafer hybrid bonding, but the most challenging with respect to the particle issue. Because the pick and place tool will physically kind of touch the die to do the pick and place. That is a risky operation. So one option is actually to place the die on a carrier first, a carrier wafer, with a temporary bonding material as a tacky glue, so you just place it quite fast. And then we clean the die on that carrier before collectively bonding to the target wafer. That's what we call with collective die-to-wafer bonding. To keep everything very clean, we use plasma dicing to singulate the die. And the pick and place operation, which is very critical, we work with the Beyne company to achieve pitches which are well below 500 nanometer in precision. So technology is getting ready to enable these type of technologies. Another technology that comes into this picture because of the high power demands and the difficulty to get a good PDN in advanced devices is actually making the power delivery from the backside of the die, especially if we start stacking memory on logic. You need to thin the wafer anyway. In this case, we go for an aggressive thinning of the silicon to only a few 100 nanometer, and then have TSVs connecting directly to the power rails of your devices. This shows an implementation of some work we did in the previous year, also integrating it with some CMOS test devices, showing that all this process of thinning down to a few 100 nanometers and making these TSVs is feasible without damaging the device performance. So to conclude, in a sense, all these different technologies, they have very different capabilities, and we put them into what we call the 3D interconnect landscape. So on the axis, you have actually the interconnect pitch, or the number of connections you can make per square millimeter. So this interconnect density that scales over these different technologies by a factor of 8 to 9. At the left side, you have the package-on-package solutions. You have then the 2.5D solutions. Then you go into these microbump stacking, which we believe can go to 10 micron pitch. The hybrid bonding, which is in the 10 to 1 micron range. And then you get into the real wafer-to-wafer solutions, which go deeply sub-micron, we believe, for interconnectivity. As a matter of fact, at the furthest side on the right, you have what we call CFET, which is the stacking of the transistor N and PMOS on top of each other to really also get substantial additional scaling at the standard cell level. Of course, this is not like a traditional roadmap slide. Each of these technologies has a kind of time arrow. There is some competition and some change over time. And we believe that all of these technologies will have their place to make the final system. If we look at where industry is today, this is showing the time versus interconnect density map. We see that die-to-wafer microbumps have been very traditional, is starting to scale only now. There was one product announced actually almost 2 years ago now, which goes to 25 micron pitch. There is the die-to-wafer hybrid bonding that was introduced by AMD. And in the wafer-to-wafer bonding, especially in the imager side and also 3D NAND, they are approaching the 2 micron level. At imec, we've been working for more than 10 years on some of these technologies, and these graphs show the work we are performing at imec and our roadmap over time for die-to-wafer microbumping going to 10, 7 micron pitch, die-to-wafer hybrid bonding at around 5 micron today, wafer-to-wafer hybrid bonding 700 nanometer today, going towards 400 nanometer pitch, and backside PDN, which is the ultimate TSV, what we call nano TSV, going to 90 nanometer diameter and scaling down to 30 nanometer width structures. We believe these are actually also the directions the industry will take in the next decade. As a research institute, we have to kind of try to figure out what will be the future, whatever that may be. But we believe this is the path industry will be taking for the next generation of products. And with that, I thank you for your attention.